Welcome to our notes for 7.2. 7.2 is a pretty big section. We actually have 3 days worth of notes had we been in class together that we would have spent. So we're just going to scratch the surface today with something called the DISC method. Before we get started on calculus, if you recall, a lot of the work we do is just a modified version of stuff you already know. So why I wanted to go over with you a review of the volume of a cylinder. And we've listed that formula right here, volume equals pi r squared h. This is going to be key for us today. Take a minute, you can pause the video and then go ahead and calculate the volumes of these two cylinders. I'll pretend that you'd stopped and done it, and I'll go through them right now. So you should have set up this one, volume equals pi times. The r is from center to edge of the cylinder, so that would be 4. And then the h here represents the height of your cylinder, so that would be 0.2. I went ahead, put that in my calculator, and I called my answer 3.2 times pi. That would be an exact answer. If you went ahead and multiplied out 3.2 pi and had a decimal equivalent, that's fine too. You would have wanted to round to 3 places. Here, the only difference in the second one, hopefully you noticed, they gave me a diameter of 6, and I want to be careful that I use the radius as the formula calls for. So the radius here would be 3, and the height is 0.4. So I typed that in, and I had 3.6 pi for my volume of my cylinder. The connection here, I want you to remember back to what we called a Riemann sum. Now we are going to take our areas, and we are going to create a volume of what's called a solid of revolution. A solid of revolution is a volume formed by rotating a region, a two-dimensional region, about a given line. To start, you would need to have a region just like what we did in 7.1 where we calculated area. So here's an example of a set of regions that gave us this particular shaded area. Now imagine that you took this area and maybe you have almost like a spiral notebook here, and you're able to fling it around so that it wraps around and around and around the axis and traces out a three-dimensional object. Right? So imagine you took this area and rotated it about the x-axis. The volume swept out during the rotation is the volume that we wish to calculate. Notice that the surfaces on the left and right are circular. When you first learned to calculate area under a curve, you broke the area into a collection of small, thin rectangles. We can get the approximation of the volume using a similar trick. We can take this three-dimensional solid of revolution, and we can imagine slicing it, just like this picture down here, into not rectangles, but cylinders. And that is where our formula comes from. So if you remember back to our integrals, right, if we were finding the area under the curve, we did base times height by integrating from here to here of the base dx times the height, which depended on our function. Now that I am taking and rotating that area around a line, I'm creating this three-dimensional shape. I'm slicing it into these cylindrical pieces that are getting smaller and smaller and smaller. And I would be calculating the volume and adding up the volumes of each of them. Imagine that we took this first one. We'll take this one right here. If I wanted to find the volume of the cylinder on the end, right, I would take pi times r squared. Here, the r is changing, and we would be dependent upon where I was on the curve. So we could say something like maybe this is a right-sided Riemann sum because I'm using the function's height here to determine my r value. And the h would be the thickness of each of those cylinders. So really, this is just a modified version of the volume of a cylinder. You're calculating the volume of each individual cylinder, and the integral is our notation that allows us to sum those volumes up. If you can recall pi r squared h, you can do the DISC method. Let's turn the page. Use the example on the first page to find the volume of the solid of revolution obtained by rotating the region, the one that was on the front, about the x-axis. A quick resketch here, right? Y equals square root of x would look like something like this. X equals 4, x equals 9. The picture was on the front page, but since we can't see it, I'll sketch it back in. And the x-axis, the region that we were talking about, would be this one shaded here in green. We are going to take that and imagine revolving it around the x-axis. The best way to think about this is to think about just what you would have with area. You can compute your R value and imagine one sort of representative cylinder. Right? The R is a function of the height of my curve. So if I'm thinking about pi r squared h, and I'm thinking about Riemann sums, but this time with cylinders, then I can modify, I can use that formula on the front to set up the volume of this object. So I would want to think about on my bounds, where am I starting to build cylinders? Where am I stopping? In this picture, that would be from 4 to 9. I would have my pi. Now pi is a constant, so I put it out front. The R, I can see in the picture that the radius is coming from the axis of rotation, the x-axis, and the R would take me up to that curve. That curve was the square root of x, and it's pi r squared. And then the h here is representing the thickness of each of your cylinders. And in this particular problem, that would be dx. It is the measurement on the x-axis of that very, very small length here, because we want to imagine that we're building an infinite number of cylinders. So I can rewrite this as pi times the integral from 4 to 9, square root squared would just give me x times dx. A nice simple one here. This would come out to be pi times x squared over 2. And if I'm using just my own brain here, I'll plug in my 9. So what's that? 81 over 2 times 4 squared is 16. So that would be over 2. And that's all times pi up front. 81 minus 16, let's think about it. That would give me 65 halves times pi. Again, when you're doing your homework, I am totally fine with you showing your setup. I would like to see it at this phase here because it tells me that you understand what was the R value. We'll move into some where the R is quite a bit more difficult to figure out. And so setting it up like this is helpful for me to see your logic and your thinking. If we're using a graphing calculator, you are by all means welcome to stop and give me either the final answer or the decimal equivalent. This one would come out to be 102.102. And like the last section, there are no units in the question, so do not worry about writing units cubed in the answer. It's not necessary. Do me a favor, hit pause and try the next one on your own. See if you can figure it out. If you do that and then come back, tune back in, and we'll go over it together. So compare your answer, right? We have this parabola right here, y equals negative x squared plus 4x. I drew a quick sketch. Maybe you did yours by hand, maybe used a calculator. It has zeros at 0 and 4, so it looks something like this. And let's see, we want the area bounded by this parabola and the x-axis. So that would give me this region right here. I want to imagine rotating it around the x-axis. That takes some imagination. I really wish we were in person. I have some physical models that I could show you here, but unfortunately, I don't have that luxury. I'm sure if you go on Khan or if you Google disk method, you'll probably be able to find some visual models. So anyways, you don't necessarily need to see it or even sketch the three-dimensional equivalent. What you really need to do is imagine just creating one of those cylinders so that you can see what the R should be. Here you can see R goes from axis of rotation to the function itself. So I would set up that the volume is pi times. My integral would start at 0 and end at 4, the x bounds for that region. My radius is dependent upon the parabola, so I would take minus x squared plus 4x quantity squared. Parentheses are important. Make sure you have them. And then the h would be my dx. It's that tiny little thickness of each of the cylinders. You can do this one by hand. It's going to get a little messy. So let's just jump to our calculator, a little refresher course here. We've got math number 9. I'm going to enter in from 0 to 4. Now I forgot the pi, so don't let me forget to multiply at the end here. I need another set of parentheses, minus x squared plus 4x. We'll close it out. We'll add our square because the outer set is really attached to this dx. When I press enter, I should be getting 34.1. We'll go to 3 decimal places as always. Oh, and I did exactly what I told you guys not to do, right? Which was to forget the pi. So that gave me the value of the integral. Now I need to remember to multiply it by pi, which is 107.233. And there's my final answer. They're kind of fun. We can also do these with rotations around the y-axis. So rotating around the y-axis is a very similar method. The formula does not change whatsoever. It's just that I would consider everything in terms of my y values. So let's try one of those, or two. I'm going to make a quick sketch here. We want to look at y equals x squared minus 1. And let's see, that would look something like this. -1 down here. Y equals 3, not drawn to scale. And y equals 8. And then we have the y-axis going here. So I would want to consider the region bounded by or fenced in by those 4 curves. Sometimes I'll have kids think about the sketch going in both directions and being confused about which. It actually does not matter. Just do not use the whole thing. You only need to rotate 1/2 because when you rotate around the y-axis, notice in the directions this time I'm rotating around the y-axis. When I do that, it would sort of land on top of itself. And I want to take 1/2 of that image and think about rotating it around 360 degrees and it land right back on top of itself. So when I go to set this one up, I want to use this method or this formula right here. It's essentially the same thing. My volume would be pi. This time though, because my cylinders need to go this way, I know that when I sketch out one representative cylinder, the tiny little thickness is measured against the y-axis. It's a vertical thickness, right? It's going up and down. And so this is what makes this a dy question. In general, when you have a vertical axis of rotation, you would use dy's. When you have a horizontal axis of rotation, you would want to use dx's. So here, I'm going to think about it as, let's see, volume equals pi. Now, r would be the length of this segment from the axis of rotation to my curve. The problem is that I need to express it in terms of y. So I need to take my y equal to x squared minus 1, and I need to write that as an x equals function. So that would be y plus 1 equal to x squared, or x equals plus or minus the square root of y plus 1. Now in my image, my x's are positive because I'm on the right-hand side of the plane. That would mean that when I plug in a y value, in order to move to the right, I would be choosing the positive portion of this function. So the equation for this half of the parabola would be x equals positive square root of y plus 1. And that is my Whoops. Hold on 1 second. I know I brought home some whiteout. Of course, I can't find it. Well, we'll make do. Plus 1 squared. And then dy. Now, because everything is in terms of y's, I want to think about I'm building disks from the bottom level here at y equals 3 to the top height here at y equals 8. And that means that I will have bounds from 3 to 8. Those are y values that I'm referencing, as is the y's in the function, as is the dy. And then you can go ahead and put this into your calculator. So I have got, let's see, this time I'm going to remember to put the pi ahead of time. Math number 9. We went from 3 to 8. And I'll do a little bit of work in my head. If I square the square root, I'll just have a variable plus 1. And then my dx here. My calculator, again, does not care what the name is. The 7 bumps the 1. So we have 102.102 as our solution. Go ahead, you could hit pause and then maybe fast forward through my explanation here, but try the next one and see how it goes. If you recall graphing logarithms, right? So y equals log of x. Logarithms have a vertical asymptote at 0. It's going to come up and look something like this. Y equals 0, that's the x-axis, and y equals 1 would be right here. Oh, I graphed the wrong thing, and now I really, really do need my whiteout, of course. Let's see. Let's see. I know I can edit this in just a minute. I'll be right back. Sorry, guys. Thanks for your flexibility and patience. I'm not exactly working at my desk these days. There we go. Y equals 1 is a horizontal line. You guys probably caught that even before I did. Y equals 1 should be going this way. And what that means is that my region, right, it needs to be bounded by log x, y equals 0, y equals 1 on the y-axis. My region kind of looks, it is this portion right here. And I'm rotating it around the y-axis. Again, you do not need to sketch the three-dimensional shape. You can just sketch and think about one of these tiny cylinders. Each cylinder, I always think about it, they have to sort of parallel. That's why I always draw the loop here. My cylinders are going to be parallel to that one. So my cylinder is going to look something like this. And that reminds me that I'm dealing with a dy problem because the thickness is in the y direction. So for this one, you should have set up volume equals pi times the integral. We're going from the height of 0 to the height of 1. And I've got, let's see, we have to express it in terms of x equals. So that would make this one e to the y equal to x. I used exponentials, e to the y squared, and then we have dy. When you type that into your grapher, you should be getting 10.036. Maybe I'll show that one just because we're not together today. If I were to type that one, I would have pi from 0 to 1. You could probably, if you're afraid of making an error, do it exactly like you set it up. Let's take our e to the x, close it and square it. Rather than typing it in as e to the 2x, I would hate for you to make an error and square your e to the x wrong. So it would look like that, and that's where I got my value from. All right, one more page. I know this one's a long video, but there's already 3 sets of videos here just for 7.2, so bear with me. The next thing that we're going to do is we're going to move our axis of rotation. So far, everything we've done, we've either rotated around the x-axis or around the y-axis. What happens if you move your axis of rotation? That is our next page. The answer is that it all boils down to some old geometry. Maybe you remember segment addition. And here it is so, so important that you're drawing a picture. Okay, so we have an example. It says that we can also consider solids formed by rotating about a line that is not one of our coordinate axes. For example, consider the region bounded by the curves y equals x minus 1 quantity squared and y equals 1. That's shown right here in 2 dimensions. And then imagine that you rotated it around y equal to positive 1. Right? It's still attached to my shape. I just, right, the axis of rotation is a boundary line of my shape, but it is not the x-axis. And the idea works exactly the same. This was their attempt at drawing a 3-dimensional model, but the idea is still the same. You would draw your radius and rotate to create these tiny cylinders. So for example, if I know I'm rotating around a horizontal line, that means that this will be a dx problem. I'll have a dx because I have the width of each of those cylinders measured along my x-axis. The problem then is how to express the radius. Everything else is exactly the same. I'm still thinking back to pi r squared h, and I'm still going to set up my volume equal to pi times, right? If I thought about drawing my cylinders, I would have the very smallest one over here towards 0, and then the very smallest one again, right? They'd grow bigger, get smaller again, and disappear when I got to 2. So we'll integrate from 0 to 2. And then I want to think about what that radius should look like. So here they've tried to draw it in. Imagine that you drew your radius right about here. That would mean that my actual cylinder that I'm interested in should have an R that was equivalent to this tiny little arrowhead. Let's think about what we do know about that arrow. I do know that there is exactly a length of 1 from here to here between the axis, the x-axis, and my axis of rotation. So whatever that R value is, it must be less than 1 unit. However, it's not equal to the function itself, because think about if you were using that particular function, my function was y equals x minus 1 quantity squared, then that would mean that if you're plugging in a particular x value, you're going up that amount to come up with, right, the point on your curve. So the function itself is always a measurement between the axis and the curve itself. So that's why they're pointing here at this piece. And the R value that I want would be the other piece. So way back in geometry, you would have talked about something called segment addition. The 2 small pieces added together would equal the whole, right? A part plus a part is equal to a whole. Or, right, if I wanted to find that smaller part, I would take the whole value and subtract the part that I know. In other words, I would subtract the function. That would give me my R value, and then I would go ahead and I would square my R. Oh, I missed a square here because my function was x minus 1 quantity squared. So I want to think about just what R is, right? It would be 1, the whole segment that I know of, minus the f of x function, and that would give me the little tiny R value. So the whole minus the part, and then that would give me my R, and then I square my R. The h, right, is the dx, the tiny little width or height of that cylinder. And you can go ahead and type that into your calculator, and you can come up with your grand total. So on that one, it looks something, I need to get new batteries, it would look something like this. We'd have pi from 0 to 2. I want to make sure that I put those outer brackets, 1 minus x minus 1 quantity squared, close it out, and square it. The interior is the R, and then I have R squared, and then there's my x. So I came up with 3.351 for my overall answer. The bottom one here is similar, but a little bit different. Let's sketch it out. We've got y equal to negative x cubed, right? So let's plop some numbers in. Let's see, if I plug in -1, if I cube -1, I get a -1, but there's a negative out front, so positive. I would cube -2, that would give me -8, but there's a negative of that, so it's way up here. I happen to know that my picture is all on this side. And then I'd come down to 0, and it looks something like this. Y equals 0, that's the x-axis. And x equals -2 would be a vertical line. So hopefully you're getting better at identifying your region. The region would be right here shaded in blue. It says that once you've found the region bounded by the curves, go ahead and rotate that region around the around the line x equals -2. So I'm going around right here. Notice that my axis of rotation is still attached. It's a full side of my region, but it is not the x or y axis. That's my signal that I'm going to need to work just a little bit harder here. Let's think about what our r is, because I know that the general formula is still volume equals pi times. I need to figure out the r value so I can have r squared. The other notable thing here is that if I think about creating one of those representative cylinders, right, because it is going around the y, or around a vertical axis, this should be a dy problem. So I want to keep that in mind when I select my bounds, right? This one would have its largest cylinder at y equals 0, and at the very top, I would lose my cylinders at y equals 8. The r value, right? If I just thought about the function, you can even practice and plug something in, right? If I, let's see, we want to take this one and say that -y is equal to x cubed, or I'm going to need a little more space here. That was a poor placement choice. Let's see, if y is equal to -x cubed, then -y is equal to x cubed, and we would have -y to the 1/3 equal to x. If I picked a y value, for example, let's pick 1, right? If I pick 1, I would take -1 and the cubed root of -1, and it would tell me to move over to find my curve. So the function itself, -y to the 1/3, is really this blank space between the axis and the curve. And my r needs to be, right, inside that curve. So knowing that the total length here is 2 units, I'm not going to pay attention to the negative, right? It should be a +2, and then I would subtract the y value. So in this one, I'm going to have, let's see. Oh, this one I've got to be a little bit careful because my value would already be negative, right? So I don't want to subtract it. I want to add the negative, right? This would send me backwards. So I would be getting a negative length. So I'll have 2 plus whatever that negative value is, -y to the 1/3. That would be my r value. And then I want to square my r and multiply by the height. So that is my setup. I know I kind of made it a little unclear here, right? But if I'm considering this to be 2 units in length and my function's already going to kick out a negative number, then adding that negative will decrease my 2 and make it smaller than 2. So I don't need to subtract on this one. Drawing a picture or plugging in a specific number is sometimes very, very helpful. I went ahead and I typed that into my graphing calculator carefully. You should be getting 10.053. And it looks like I left it off here, but I know it is on the assignment sheet that I'm sending out. It's page 463. You've got 1 and 3 and 7, 9, 11 do parts A and C, 27, 31, and 35. I would suggest that before you move on to the next video, go ahead and work on the disc method first, and then you can move on, because the next method is a little bit trickier than this one, and a solid understanding of what you're doing here will go a long ways in helping you to set up. This is probably the most important work, and probably the hardest to do given that we're not together. So anyways, keep working on that. Try the Khan videos that I've linked up in case you need to see more examples or just hear another voice trying to explain it. And this is something we would definitely talk about again once we've all returned to school. Thanks for watching.